Yeah, so we will begin with today's class. Good evening. Today we will be mainly covering the contents of week 4. So, week 4 of your ME75 Foundations of CFD, that is mainly on the finite volume discretization for your convection diffusion type of equations. So first we will just briefly recap the contents of previous weeks, and then we will try to get a physical understanding of what is convection, what is diffusion, and why they come in the governing equation and how they affect the solution. We will try to understand that, try to get a physical appreciation, and then we will try to look at the governing equation, and then how we can try to come up with a linear algebraic equations using the finite volume discretization. So that we will try to see today. And once we get the linearized algebraic equations, there are many methods through which we can solve them. So mainly we will not discuss those methods. We will just come till the linear algebraic equations for both pure diffusion problems as well as problems involving both convection and diffusion, and mainly for 1D and 2D. Okay. So then we will try to look at some assignment type of problems. Some 6 to 7 I will try to solve today. Okay, so after that, today we will be solving a 2D heat conduction problem using finite volume method. Okay, so mainly in the last class we had seen a 1D heat conduction problem using finite difference method. Okay, where we had solved using the explicit time marching scheme with FTCS and then with Dufault-Frankel scheme, and we saw that how a small change in the code can make an stable uh, conditionally stable scheme to unconditionally stable scheme. Okay, so today we will be trying to solve a 2D heat conduction equation but using finite volume method. So there is a quite a bit of change when you go to finite volume method as compared to finite difference method. So we'll try to see what are those changes and how the code now changes. Okay, the code gets completely changed now. Okay, and we will try to see a steady problem. Okay, not a transient problem. So here we will not deal with the explicit time marching or implicit time marching which we had discussed last week. So as I said last week, the steady state problems offer a bit challenge to solve, I mean coding wise, whereas transient equations are easy to solve, especially with explicit time marching. Okay, so we will try to see that challenge today by not taking unsteady term. We will try to solve only the steady equations. Okay, so we will write a code in MATLAB at the end of this class. Okay, just to illustrate the working of finite volume method. Okay, so first let me come to the brief recap. Okay, so mainly till now you had studied the governing equations which exist in CFD, basically the flow conservation equations, which are the mass conservation, the momentum conservation, and the energy conservation. Okay, and then the non-dimensional form of those equations. And then in the second week we mainly saw the Taylor series and how we can just convert these partial differential equations directly into linear algebraic equations using this Taylor series formulation. Okay, so that was the basic formulation. Now using this we also looked at finite difference method mainly in the previous week, how it uses these Taylor series which we had studied to come up with linear algebraic equations for. Mainly we saw again the diffusion equations itself in the last week, and we were also introduced to finite volume and finite element method, but we delved more into the analysis of the scheme. So for example, if I am doing a particular kind of time marching for the transient equations, whether I will get a stable solution or not. So that we were trying to see using the von Neumann stability analysis in the last week. Okay, so that was the main thing, and also we kind of touched upon what are the different errors which exist when we come up with a discretization scheme and then when we try to solve those things. Okay, so we were overall we were kind of trying to see how we can apply finite difference method, okay, and which schemes are kind of more stable and so on. But from I think from week 4, I think the journey slightly shifts here, and it becomes more important now, in the sense that we are introduced to finite volume method, and finite volume method, as I said last week, is a more robust method because you can handle complex geometries also very easily with finite volume method, okay, which is not possible using finite difference method. So we are introduced to finite volume method in this week, and we have seen in the weekly content, okay, we have seen in the weekly content how to solve the 1D and 2D diffusion convection. First we saw diffusion and then convection diffusion equations. 3D was also touched upon, but not to a great extent. So that was mainly the whole recap, I would say, of these weeks. So first of all, before getting into the equations of this convection and diffusion, we have to try to understand what they physically mean, okay. So that I will try to explain using the energy equation. In energy equation also we will have diffusion terms, we will have convection terms. Now we will try to kind of understand the physical relevance, okay, before going into the governing equation and then the discretization, okay. Okay, till now, are there any queries? Okay, regarding what we have discussed, mainly the recap of week 4 contents and the previous weeks also. Okay, if there are any queries, just write down on the chat box. Okay, okay, if there are no queries, let me just share my screen. Okay, so is my screen visible? Can you guys write down on the chat box if my screen is visible? Okay, thank you, Vikas. Okay, so what I was saying is that, see, you have two parts in any governing equation, the diffusion part and the convection part. I mean, in the weekly content you might have seen the equation also for that, but I just want to touch upon some physical relevance of that. Okay, so let us try to see it using the energy conservation equation. Okay, so assume that there is a kind of block of ice on the right side. Okay, now this is at 0 degree Celsius. Now in the left side, assume that we have some fire which exists at say some 100 degrees Celsius. Okay, so now assume that you are standing, okay, somewhere in between. Now assume that there is no airflow which is happening. I mean, the air is stagnant in the atmosphere. So ideally, what would you experience? I mean, what kind of temperature would you experience here? I mean, you as a person who is standing in between at exactly in the middle, I mean, what kind of temperature will you expect to experience? Can you write on the chat box? There is no airflow which is happening, okay? Can you write on the chat box? Room temperature in the initial time, but after some time, Initially, if there is fire and if there is a block of ice, and if you are standing in between at T is equal to 0, maybe you might experience room temperature only. But after some time you have to experience either hotness or some coldness, right? I'm just saying that there is no airflow in this room. Okay, if there is some room, if you can imagine, okay, there is no airflow which is happening. Okay, so just let us try to see what type of heat transfer will occur here. Okay, will there be any convection here? What I am saying is that there is no airflow. Okay, so there won't be any convection because your convective heat transfer is mainly driven by this bulk motion of fluid particles. Okay, now that is not happening here. Okay, because I am telling that air is stationary. Okay, so that won't happen. It's only a pure diffusion process, or you can say conduction here. For a temperature thing, for energy equation, it's conduction, or in general we call diffusion. Okay, so mainly after some time you can expect to be at, say, a temperature in between 100 degree and 50 degree Celsius. Okay, after some time, say 1 hour. Okay, so after that you might expect to be at temperature which is exactly half of 100 and 0. Okay, 100 plus 0 divided by 2. Okay, so it's like a pure kind of conduction problem. If you have a rod and kept at 0 degree and kept at 1 and kept at 100 degree, which we saw last week also. Okay, so it's there will be some kind of linear variation. Okay, in the temperature, so that we have seen, right? So it is a kind of pure diffusion process. Now in the second case, let us say I have a fan placed here in this room. Okay, and the wind is being blown at, say, 10 meter per second. Okay, what can you expect this temperature? Will this be less than 50, or will this be more than 50 degree? You will experience temperature more than 50 degree, or you will experience temperature less than 50. Can you write down on the chat box? More than 50, right? Because you will get more heat because the fan is being blown with some say speed, and this the heat from this fire tries to reach you quite faster than the coldness from this ice block. Okay, so here it involves convection. Okay, because there is a bulk motion of fluid particles and they carry the heat from this fire towards you. Okay, now usually what we do, if you assume that this is one grid point, even in FDM or FVM, whatever it is, and this is some other grid point, and say if you want to try to calculate the property at this phase. Okay, now generally we do averaging. Okay, but you have to understand, when there is some situation like this, when there is convection which is happening, you cannot purely do an averaging of temperatures. Okay, so that is what I wanted to mainly emphasize here. Now in the reverse case, if the fan was placed, say, on the right end, okay, and it was blowing wind at again 10 meter per second, you would feel temperature less than 50 degree. So it depends on two things. The convection here, can you write down on the chat box, what does it depend on? I mean, the temperature of this person who is standing in between will depend on two things. Okay, one thing I think I have already told here. Can you write on the chat box which are the two things on which the temperature of this person standing in between will depend upon? Okay, assuming that I am blowing the wind from the fan. Okay, assuming that there is convection. one thing is definitely, I mean, temperature gradient, by which you want to say what is the temperature here at what is the temperature here. Yeah, that is definitely a thing to consider. If we have say more temperature 1000, then definitely this will be more than 50. Yeah, but only in context of convection if we see. Okay, the two things which will mainly yeah, I think Sivakumar has written, yeah, flame temperature and ice block, that is what temperature gradient I would relate it to. And then the direction of the airflow, that is very important. Okay, as I said just now, if you have a fan going from here and in the other case fan going from the right side, the temperature experienced by this person is completely different. Okay, so it depends on direction of the flow. Okay, that this one thing you have to keep in mind. I mean, this is very important. Okay, we will see why when we come to advection schemes. That is one thing. Okay, direction. Also, not only direction, it depends on magnitude of this velocity also. Now, if I had the air being blown at say only at 1 meter per second, okay, again this would not matter much. Still, the person would feel the temperature somewhere near to 50 only. Say he would say 45 or something like that, 45 degree or something like that. Whereas if I blow the fan at say 100 meter per second, there is a very large chance that this person will feel temperature near 0 degree. Okay, it would be near 0, that is it would be 10 degree or something like that, 10 or 20 degree. So it depends on direction of the airflow and the magnitude of the airflow also. Okay, so that is what defines this your convection part. Okay, so keep this in mind. We will again come across this when we try to see the equation and when we try to do the finite volume discretization. These things are very important to be kept in mind. Okay, now so this is a physical relevance. Okay, these are the physical relevance. Okay, now the main in the equation you get the rate of change of temperature. Okay, with respect to time, and then you have an advection part. Okay, now in typically in governing equation, I'll just write for 1D. Okay, here now you have u into dou t by dou x. Okay, as I said, the velocity will come into picture here. Okay, now this is equal to the diffusion part, k into delta square t by dx square. Now typically what we do in finite volume method is we generate something called as control volume. Okay, within our domain, say this is my square domain. Now I divide it into three equal blocks. Okay, in y direction and three equal blocks in x direction I am dividing it into. Okay, now at this with this particular small red square is a control volume. At the center of this control volume is the centroid of the control volume. Okay, I think it is termed as node in your weekly content. I mean, the terminology is given something like that. There are different terminologies, but try to understand the just the concept. There is centroid of the control volume. Okay, so similarly, I will have 9 centroids. Okay, for this. So what I intend to do is over this whole control volume, the integral of this equation, governing equation, should be satisfied. Okay, so what I do, I just integrate. Now if I assume steady state, this will go to 0 anyways. Okay, now so the integral of your u into dou t by dou x over the whole control volume is equal to, actually it is d by dx of k dt by dx. Assuming k to be constant, I had removed it out. Okay, your from your Fourier law you get it like this, k dt by dx into control volume. So this is the general equation. I think you might have not seen this equation in your weekly content, but this is how we derive it actually. Okay, so this is the partial differential equation which you all very much are known to. Okay, but from here you have to understand things. Okay, now what usually is done in finite volume method, and I think this maybe this step was somehow in the notes, it was not there. Okay, we do apply something called as Gauss divergence theorem here. Okay, especially when we have kind of the gradient terms. Okay, so here also the gradient is there, here also the gradient is there. Okay, so this volume integral now it can be converted into a surface integral. Okay, I mean you might be very much well aware with this Gauss divergence theorem. Okay, gradient of phi into dv, where v stands for volume. Okay, here not velocity, volume is equal to over the volume is equal to surface area, the integral over the surface area of phi dA. Okay, so this is how it comes in. Okay, actually it is phi n dot dA, it will be. Okay, it will be a dot product of area and its normal vector. Okay, so in that way we convert this equation. Okay, and then I think it was written right like this. So this k was assumed as a diffusion constant, and then you have divergence of phi and dA. Here also you had u into t direct only dA. Okay, now I think I don't remember, u was written as uh, no, u was u only, I think t was written as phi. Sorry, t was written as phi. What I saw, I think, okay, whatever it is, so that you have to understand this u is u only, temperature, or in Navier-Stokes we get phi as velocity. Okay, so that is why in general t is written as phi. Okay, so this is your typical let me just make it proper. This is just nothing but u and phi. Okay, into d. See, this is your typical what you see the convection diffusion equation in the integral form. Okay, this is in the integral form, and this is what we use for finite volume discretization. Okay, any queries till this part? This derivation you should be knowing. Okay, because if you are given some different equation, okay, there might be some extra terms and all. You have to understand how you came up to this equation. I mean, that is very important. After this we will do the discretization, convert into linear algebraic equation. That is not a much challenging task, but in CFD the main challenge is like why still CFD exists. There are so many softwares like ANSYS, COMSOL. Still the development things goes on. Okay, because you have some changes in physics. Okay, changes in physics will lead to changes in your governing equation. There will be some small addition of terms. Okay, and for example, let me give my own example. So when we kind of do the blood flow in a stenosed artery. Okay, say I will solve the Navier-Stokes equation to find the blood flow patterns and all. Okay, that is fine. Now one thing is I can try to get the plaque concentration also. Okay, the low density lipoprotein concentration which already exists in blood. Okay, where it will go and where it will stay for more time in this artery and all. So through that I can understand where the further this constriction can happen in the artery. Okay, so that I can try to understand even for a straight artery or straight channel also, that is possible. Okay, where in if I have say bifurcation region, in which bifurcation region I can expect to get more of this plaque concentration and all. Okay, so what will happen there is that apart from your Navier-Stokes equation, the mass conservation and momentum conservation, I have a different equation. It is called as a transport equation for just for this concentration of this plug. So now I have a different equation. Okay, now I have to come up with the integral form of this that equation and then try to do kind of discretization and write code and all. Okay, so that particular modules will not be directly available in your softwares. I mean, you can indirectly do that, but still you need to understand these things. Okay, so that is why these things need to be clear. I mean, if you are really interested in CFD development and all. Okay, so I don't see any questions on the chat box, so I hope that this concept is clear. Okay, so this is how we try to come up with this integral equation. So now once we come up with this, then we can just directly apply this integral equation on the control volume. Okay. So let me just take a 1D control volume, and 2D also it will be just a simple extension. Okay. Although I am drawing it like a 2D or something, but it is not 2D, it is just a 1D. Okay. So here I have my present control volume. This whole rectangle is a 1D control volume for this with this P as centroid, and say this is the centroid of this west control volume. I mean, the control volume still extends. I have not drawn it properly. Okay, it will still go on like this, but the centroid of that control volume, let's say E. Okay, so there are some terminologies, I mean, which you can form on your own. Okay, I don't say that you have to strictly follow this or something like that. Okay, so one thing is the distance between the two centroids. Okay, and then usually the width of the control volume. There are two geometric parameters. Okay, usually we try to denote it by delta x, and we denote it by small del x. Okay, now here it is the west surface, I call it as small w, and here the east face, I call it as small e. Now this will be dxw and dxe. Okay, so now this particular equation I have to apply on this particular control volume. Okay, this particular equation. Now basically what it will become is on this, for this control volume, this u phi. Okay, actually it will be I think rho cp will also come. I think I have just skipped it here. Okay, rho cp will also come here, so it will be rho cp into u into phi. Okay, so in general it is called as I think f in your weekly contents, f into phi. Okay, along east minus f into phi. This is just your definite integral, I mean, which you might have studied in basic mathematics. Okay, just integral of this. Okay, fu into a, dA will be also there. So integral of that. Okay, you will get a here. Here also you will get a. Okay, and then similarly you will get tau into dou phi a. Okay, east minus f phi del phi. Sorry, this is tau. Okay, del phi a of west. Okay, so this is your final equation. Now you can calculate gradient of phi along the east face, along, sorry, yeah, east face. You can calculate it as te minus tp, or general phi e minus phi p divided by this delta xe. Okay, that is how you find out this del phi, gradient of phi. And then fe and phi e you can write it directly. And the now what is very important is how do you determine this f at e. Now phi at e is temperature at e. Okay, now it has to take into account the uh, the F term. Okay. Now what is typically done here is that phi e is determined using your convection schemes. Okay, so as I said earlier, the temperature you can't just do a linear interpolation here. Okay, so you have to keep that in mind. That is very important. Okay, so see, for example, if the velocity is very high, okay, so then we typically say take only one temperature. Okay, 50 degree I will not call this as. Okay, I will just say this is 100 degree. If the velocity was in positive x direction, I mean if the u was say plus 100, it is very high. Okay, now I would say temperature at this say it is east phase. Okay, then it will be equal to uh, okay, so it is actually west phase. Okay, so now if I kind of consider this as a phase. Okay, now if I consider this as a phase, now t at west phase, that will be directly equal to tw. Or else if the u was say minus 100, okay, now what would happen? T at the west phase, that would be directly equal to t at the p, that is 0 degree. It will be 0 degree. Okay, it will be 0 degree. Here it would be direct 100 degree. So again, that is what I was telling, you have to take into account the flow direction and the magnitude both. Now I am just telling this very in a very vague manner. Okay, there should be some technical aspect through which we can kind of determine whether I need to do this kind of temperature direct interpolation, and not interpolation, direct substitution, or can I should I do a linear interpolation. Okay, so that is defined by what is called as your Peclet number. Okay, that's a more technical thing to do, I mean more better thing to do. Okay, instead of just going like this. Okay, so in your Peclet number, it is basically the ratio of your convection part to your diffusion part. Okay, FD, but I have not defined FD. I think I have only defined FC here. When you come here, F you know here, um, but generally this FD, that is considered here as your tau by delta x term. Okay, because if you what you can write it as this gradient phi as delta phi, change in phi divided by delta x for 1D. Okay, so tau divided by delta x, that will become your FD. Okay, so if this magnitude becomes very high, okay, basically what it means is that the convective term is very high. So you have to do substitution like this with a previous grid point temperature or so, something like that. So this is called as upwinding. Okay, in technical terms. Okay, I had just directly told you that here you substitute the directly the temperature of fire, or you directly substitute the temperature of ice block. So that is particularly called as upwinding scheme, and what I had told you here is called as actually first order upwind, I think. But in your I think the content, I think second order upwind and all they were present. Okay, now you can go on with that. Okay, so in general what we do in upwind scheme, how we derive that, I will discuss it during the questions. Okay, but just remember that you have to do such kind of upwindings. Okay, you have to take that influence of the temperature at upstream temperature, upstream direction. Okay, now what we call as upstream and downstream, uh, do you know, I mean do you people know what is upstream and what is downstream direction? If yes, can you write down on the chat box what is upstream and what is downstream direction? Because I will say something, but if you don't understand that, then that will be a issue. Okay, before a node upstream, after a node downstream. Is that? Others, can you also guess? Upstream along x direction, downstream against the x direction. Okay, that means I think it's the same, right? I mean before node or after node downstream. Incoming direction is upstream, yes, like towards zero. Okay, So I think Ayaz Khan has given more of a, I think, a better answer. Incoming direction is upstream. Okay. See, you have to understand this. Maybe we usually like talk in terms of positive flow, and that is why we call x direction upstream and against the x direction downstream or something like that. Okay. So, but in a more technical manner, so you have a grid point P here, okay? Then you have other grid point after the grid point or before grid point, what you are talking. Here we have W and E, okay? Now this is positive x direction, let me say x direction, okay? My x direction is like this, okay? Now if the flow is like this, I mean it's towards the rightwards, it is in the positive x direction, U is something plus 10. So basically this will be upstream and this will be downstream. Basically upstream means from where the flow is coming, as I think it was written correctly on the chat box, okay? Direction of the flow, that is the upstream, from where the flow is coming in, okay? Now as compared to your P, okay, flow is coming from the left side, so this left side will be your upstream and right side will be your downstream of this node P. Now if the reverse case was there, if U was minus 10, okay, now what would happen, the whole thing will get reversed, okay? Now your upstream will be your right side, okay, because the flow is coming from your right side, right? So where the flow is coming from, so that you have to call it as upstream, okay? So I hope you have understood, it is very important, okay? Because what happens in generally in textbooks, what people write for convection schemes, say for example if I am writing like this, and if I have a control volume like this, and if say I want to find temperature, sorry, something, the F value, the temperature at east phase for the convection part, okay, temperature at east phase, so what they will write it as, okay, T of upstream, they will write it as. Now what will you take? Now you can take E in general, if your understanding is like afterwards and before that. But you have to see the direction of flow. If the flow was in positive x direction, then that would have been correct. It would have been equal to TE. Okay, sorry, it would have been equal to TP here, because the upstream is P, okay, if it is like that. Now if the flow was in the negative x direction, then the upstream would have been E, okay, it would have been TE, okay, T upstream. So in general for first order of point it is written like this in textbooks also, TE is equal to TU upstream, okay, but you have to understand what is upstream, okay? So yeah, so we generally write the advection schemes like this, okay? So you have to take into account the advection scheme, and then decide the temperature or the variable phi. You get f phi at E, right? F phi at E minus f phi at W. You have to be very careful here. Okay, so that is what I wanted to say. Hmm? Okay, then the diffusion part is quite easy actually. I mean, you need not uh, do too much here. It will be like gradient of phi. So at the east phase, it will be TE minus TP divided by delta x. We use just uh, I mean, what is this? First order central difference, first order difference scheme. Using the Taylor series, which you had learned in the previous weeks. Okay, just divided by delta x. Okay, this is at calculating at TE. So this is a central difference scheme. Okay, it will be second order accurate. Okay, TE minus TP. Okay, here you are calculating at E, you are calculating the diffusion. TE capital E minus P divided by delta x. Sorry, it won't be delta x. It will be dx E. Okay. So similarly, again minus tau into T P minus TW divided by dxw. Okay, so this will whole complete your part. Okay, now once you do this, you will get equations, you will get like how many grid points you have. Based on that, you will get that many equations, you need to solve them. Okay, I will with an example today, we will write a code for 2D conduction and we will see how to solve that also, okay? but the main intention in the current week, that was to only come up with this linear algebraic equations anyways. So this is how you come up with a linear algebraic equation starting from a partial differential equation. Okay, are there any queries till here? So I will start with the question and answers now. There are no queries. Okay, because this was the mainly the content which was there in your week 4. If there are any queries, just write down on the chat box. Okay, I'm seeing. Yeah, Peckley number definition in terms of del x, we will see that in the question and answers. Okay, there is one question on Peckley number and how we calculate Peckley number using the del x definition. That we will see. I think if still there is some query, you can continue. Okay, I'll ask you if you still have any query. Okay, we will see that in the questions. Okay. Okay, so let us begin with questions. So I hope that this PPT is visible. Okay. Yeah. Mm. Okay, so this was a brief recap again what I have told. The mainly the integral equation, how we do the diffusion, discretization, and then combined. I actually did directly combined convection and diffusion. I mean, not separately, but in a combined manner. So the first question is as follows: for steady state 2D heat conduction equation which does not involve heat generation, it is which type of equation they are asking. Okay, I think I have discussed this in the revision also. Pure diffusion, or is it pure convection or convection diffusion? What should be the answer? Pure diffusion, because has written. What about others? What do you feel? We have discussed this, right? Yeah. Okay, let us try to see it from a governing equation perspective. Okay, physically, I think you might have directly given the answer. So this is the beauty of understanding the physical relevance. Okay, you need not go into maths now. Okay, you can just directly answer this question. But I have just written it down in terms of maths also. From math also, how can we give the answer? Okay, what you have written is anyways correct. Okay, so if we see a general energy conservation in terms of temperature, we can write it something like this as written here. Okay, so we have the temperature gradient with respect to time, temperature change of temperature with respect to time, and then we have the incoming advection flux. Okay, and then the diffusion flux. Okay, and then the q generation part also comes in. Okay, so why this comes on right hand side and why this comes on left hand side, I hope you might be knowing, because this is incoming. We usually take it as incoming advection flux and the total diffusion flux which is going out of the control volume, so that is why it comes on the right hand side. Okay, so I think that is understood. Okay, so now the first condition is steady state. So capital dou t by dou t, it will go to 0. Okay, so that is the meaning of your steady state. Now the heat conduction part, it is only heat conduction, so it means that the convection is 0. So basically your u dou t by dou x plus v dou t by dou y is 0. In reality it is just u and v 0, so totally this part will become 0. U dou t by dou x plus v dou t by dou y, that would become 0. Okay, now the third thing which is given is 2D heat conduction without heat generation. Okay, So again, that is your fusion is equal to 0. Now what is remaining? What is remaining is just this term, k into dou square t by dou x square plus dou square t by dou y square is equal to 0. Now if I kind of apply the finite volume integral on this for this equation over the whole volume, and then if I do the Gauss divergence theorem, that part I have skipped here, okay, but I have explained it previously. So I will end up with this equation. This typically resembles your the gradient of your temperature phi over the area integral. So that is your pure diffusion equation, right? So yes, the answer is pure diffusion. You all have already said it, I think, because um, you understood like by just the physical relevance. Okay, so heat conduction itself means that there is no convection, so it should be a pure diffusion equation only. Okay, just I would ask one question here: is a pure convection equation possible? I mean, the second option is pure convection. We have seen that pure diffusion is quite easily possible. Is pure convection really possible? Can you write down on the chat box? It is possible. No. So I am getting a mixed answer here. When Peclet number greater than 10. Okay. So Shiva, was it written in this weekly content that Peclet number greater than 10 it is pure convection? I don't remember reading, but maybe it was written. So is it written there? I mean, Shiva, can you answer? When Peclet number greater than 10, you are telling it is pure convection. So was it written? Okay, you are telling that. Okay, diffusion can be neglected. Okay, it was written. Okay, okay, I don't see it. Okay, but that makes sense. Okay. Uh, I mean, in reality, if you see, a pure convection is not possible. Okay, uh, because there will be some amount of diffusion, but it's always when we do maths and when we do governing equations and when we try to solve them, we try to see which things can we ignore. Okay, so it saves a lot of time without changing the results. Okay, you will get just 0.1% error. I mean, in cases where Peclet number is greater than 10, if you ignore diffusion term, you will get only 0.1% or less than that error. Okay, I mean the difference will be just 0.1%. Okay, so you can definitely ignore the diffusion part, but in reality, if you see, you will not get a pure diffusion process. Okay, sorry, pure convection process. But in mathematical sense and in governing equation wise, pure convection is possible. Okay, I mean you can solve a pure convection equations. That is what I am trying to tell here. Okay. Okay, so that was just a additional thing. Yeah, so it should be pure conduction. Sorry, what? Pure diffusion. Okay. So the general form of discretized 1D heat conduction equation via FVM is so and so. AP TP is equal to AET plus AWTW. The value of AP should be. So you have to understand here the general form of discretization of 1D equation. They have written. They have not written. Heat conduction they have written, but they have not written whether heat generation is there or not. Okay, when something is not written explicitly, you have to consider that it is already there. Okay, they have not given whether heat generation is there or not. Okay, so let us consider that there is a source term. Okay, considering that, you have to give the answer. What should be the answer? I think this was there in weekly content, but anyway we will derive it again. Since I have told that heat generation should be there, so I think so one option is already removed. I think two options are on. I mean removed from this. A. What about others? Vikas has written A. So okay, so let us see. In the weekly content also this was there, but I think there was some slight error in that. Okay, so let us see what will happen. Okay, so this is your what do you say, conduction equation in one dimension with source term. Okay, I have written source term here as S. Okay, now as I said, the source term again will come on the right hand side only in the previous equation. Now I have brought the whole thing on left hand side. Okay, so it is k d square t by dx square plus S. Okay, is equal to 0. I hope this is quite clear. Now I am doing the finite volume integral. Okay, so that is a regular process for me. Now S delta V, I will just write it as SP into T plus SU. I think this was also there in the weekly content. So what we are trying to tell here clearly is that the source term may be a constant, or it may depend on the temperature, or it might be a combination of both the things. Okay, so that is the meaning. Source term is a depend. See, like for example, heat generation, it might be again a what do you say, function of temperature itself. Okay, in some cases. So for example, if I have a wire, okay, now a wire will produce some heat, which is given I think by uh, I square or R or something like that. The heat generated by a electrical wire, which, I mean when it carries current. Okay, I square R. Now R is a function of temperature. Again, resistance is a function of temperature for wire. So the heat generation can be a function of temperature. Okay, so in general we write it like this: constant plus function of temperature. Now if you see in all the options, they have not given anything about SU. So maybe the SU can be 0. Okay, so just ignoring SU, let us see. But in general, I have written SU also here. So this whole equation becomes turns up like this: Ka into dt by dx E minus Ka dt by dx W plus Su plus SPTP is equal to 0. So let us see what happens next. Okay, so I am just expanding this Ka at east phase, and dt by dx, as I said earlier, along the east phase, if you see central difference, if you apply, it is capital Te minus Tp divided by delta x. It should not be delta x, actually it is the small dx as per as a convention, but okay, I think this was there in weekly content, something like this convention, delta x pe, okay, fine. So this also will go like this: on the west face it is Tp minus Tw divided by delta x Pw. Okay, I hope this is clear. Okay, so as I said, right, the heat generation or the source term in general, okay, um, is, it is a source term, right? Like previous, I think in the previous equation I had written that. Okay, you have a source term on the right hand side, right? So that time you had a heat generation term, right? That I'm writing it as source term, yes. That I'm writing it as yes. Okay, now S can be a it can be a constant also, or it can be a function of temperature also, like I said, the electrical wire thing. Okay, so we just write it as a linear function of temperature. Now again you can write it as T square and all, but in general we just take it as a linear function of temperature, the source term, and then a constant also. So that is the meaning of SP and SU. uh, I'm really not sure why it is called SU or SP, something like that, but that is the meaning. Okay, I don't know. I am not able to guess also. Like, but what the meaning is that basically it means that it is a function of temperature, and U is SU is a constant source term. Okay, so that is the thing of SP and SU. Okay, I will have to see why the underscore, I mean the subscript P and U have come. Okay, I really am not quite familiar with that terminology, but anyway, so that is the meaning. Okay, so if we expand it again, okay, just taking the TE TW terms, keeping it on the left hand side, and I'm just shifting the TP terms, coefficients of TP on the right hand side here, if you see. Okay, so because TP is associated with minus sign, okay, so that is why I'm shifting it to right hand side, so that it kind of becomes positive and all. Okay, so now you have to clearly see that it becomes the SPTP. If it goes on to right hand side, it will become minus SP into TP. Okay, so this is your AE, AW and B term. again, as I said, there is no B term here, so I think they have taken SU as 0 or something. Let it be AE into TE plus AW into TW. Okay, and your this thing AP into TP. Okay, now again, one more thing, I think it should be capital E and capital W, I mean for temperature, and say this also anyway, but that is fine if you are writing small or capital. But I mean, when we do a terminology, we always say small letters are associated with phase and capital letters are associated with your centroid point. So it should be ideally the capital letter here. Okay, so anyway, so AP, if you see, it will be a combination of this AE plus AW. Okay, AE plus AW, and it will be minus SP. Okay, so the option number 2, that is correct. Okay, here it's not plus SP. I think in the weekly content it was written plus SP or something like that. But from the way in which it has come in the weekly content, this was there, SP into T plus SU. So it is not minus SP into T, it is plus SP into T only. So if you take that, then minus SP will only come in. Okay. So is this understood? I mean, because some of you I think had written plus SP as the answer. So just be careful. It will come minus SP actually. Okay. Okay, I hope that this is understood. Okay, so you can expect such questions in your exam, but I hope that they just give it clearly, because TE will make some confusions here. Okay, I don't know what TE is. It should be capital E. Okay, so next question is a bit simpler. Okay, okay, I showed up the answer also. While solving a 1D heat conduction equation without heat generation using finite volume method, what kind of matrix is formed? So this is quite related to your previous question. Okay, if you see the previous question, you will get the answer for this question. Okay, in this you are written AP into TP is equal to AET plus AWTD. This is also for 1D heat conduction. Okay, now without involving a heat generation, so SP is also 0. Okay, so what kind of matrix will you get for such an equation? Can you write down on the chat box? For such an equations, what kind of matrix form you will get? I hope first of all you know about the matrix forms. Okay, so in your linear algebra course you might have studied this. Yeah. What about others? Only one person has answered. I can see that. Okay. So you will get something like this equation. Okay. So for your node 1 and the west coefficient will not come, because you already know the west temperature. Okay, that you will just put it in the b term. Okay, so don't worry about that. So AP AE only you will get, and in from the second until n minus 1th node point, you will get all AW, AP and AE, right? So that is what you had studied in the previous question. So only three elements will come, all are 0, and in the third row also similarly three elements will come, all are 0. Okay, similarly in all the rows you will get only three elements, AP, AE and AW. All the other elements will be 0 in this matrix, in that row. Okay, so only three elements are there, so that is called as a tridiagonal matrix. Okay, so the answer is tridiagonal. Now what if you are having 2D heat conduction equation? What kind of matrix can you expect? Can you write down on the chat box? Yeah, it should be a pentadiagonal matrix. Okay, because apart from AE and AW, you will also have AN and AS, A north and A south. Okay, so you will have a pentadiagonal matrix. Okay, uh, so that is the second option is true for 2D heat conduction. Okay, anyway, so this type of matrix systems are very easy to solve. Okay, we have something known as direct algorithm, a direct method to solve this to get TP. There is something called as Thomas algorithm, which you can, I mean, go through if you are interested. Okay, I mean, there are many methods to solve this system, but it's a quite an easy method wherein you will get direct solution. Okay, so I'll just discuss this when we are writing the code. Okay, today. But anyway, so the tridiagonal should be the correct answer. The convection term in Navier-Stokes, yeah, I have discussed this in the starting now. Now, all of you should answer this question. What should be the answer? Convection term is influenced by which of the following? Okay, yeah, so it is influenced by the flow direction as well as it is influenced by flow magnitude also. Okay, so that is not there in the option. So okay, but it is influenced by both flow direction as well as flow magnitude also. Okay, it is influenced by both. Okay, so anyway, I have written that F is influenced by flow direction as well as flow magnitude. Okay, so that is what I was trying to tell here. Now the diffusion term. What is the diffusion term influenced by? What should be the correct answer for this question? Can you write down on the chat box? Okay. Yeah, B is correct, but C is also correct because we do not get any velocity terms in the uh, in this diffusion term, right? So it is independent from the flow direction. That is also correct because we do not get any velocity terms here. Okay, this I have written for x momentum in your Navier-Stokes. You just get dou by dou x into mu into dou u by dou x plus dou by dou y of mu dou u by dou y in for a 2D. Okay, so you don't have any velocity terms here, right? So it is independent from flow direction. I mean flow magnitude and direction, it is independent. Okay, so it is influenced only by the gradient of this temperature. Sorry, velocity here. Okay, so B and C, that should be the correct answer. Okay. Now coming to the Self-Peclet number, I think which Siva had already asked the question regarding that. We will slowly move into it. So what is Self-Peclet number? What should be the answer for this? The Self-Peclet number is a ratio of what and what? I mean, I have already discussed this during the revision, I think. Yeah, it should be the ratio of the convective to the diffusive flux. Okay. Now again, as I said earlier, if the Self-Peclet number is very much high, I mean in general, it is taken if it is greater than 2, then we go for upwind schemes. Okay, so wherein we don't do linear interpolation, which we do when Peclet number is less than 2, but we don't do this between the two cell points. We select only one, or before that the say upstream of upstream. Okay, so that we take it. Okay, so anyway, Peclet number is a ratio of convective to diffusive force, so that should be the answer. Anyways, okay, okay, so this is a bit involved question. Okay, so in a 1D convection diffusion problem, how many points are used in a quick scheme? Okay, first of all, um, do you guys know the full form of quick scheme? If you know the full form, can you write down on the chat box? Because from there only we can go about derivation. Yeah, if you don't know, write no also. Okay, no problem. Quadratic central. Okay, good guess, I would say. Okay, fine. Yeah, that's great. But anyway, your concept is correct. Okay, you need not remember the full form. It is actually quadratic interpolation convective kinematics scheme or something like that. Okay, C is for convective and K is for kinematics, but it is QU is something like quadratic. So again, what I wanted to say here is that it is a quadratic scheme. Now a quadratic function always looks something like this: t is equal to ax square plus bx plus c. Okay. Now how many coefficients are there here? There are three coefficients, right? A, B and C. So this is a quadratic equation. So to obtain three coefficients value, how many equations do I need? I need three, right? Three equations I need. So say for example at x equal to 0, I have to know some temperature. At x equal to delta x, some temperature. At x equal to minus delta x or 2 delta x, I need to know some temperature. Okay, then I will come up with three equations. Then I can solve those three equations to get this value of A, B and C. So that is how I come up with the temperature value in the quick scheme. Okay, so that is the derivation. You should never remember the formula for this temperature, how you will calculate using quick scheme. Okay, these are called as weights. So usually people try to remember the weights of the temperature at different node points. So don't do that. Okay, try to derive it. It is very easy. Okay, so we need 3 points, right? So three nodal points temperature value we need. So that is the answer for this question. How many points are used? It is 3 points. Okay, but let me also explain the derivation, and this is a general derivation. You can apply it for second order up point also. Okay, I don't know whether this was there in the weekly content or not. As far as I saw, I did not find it. Okay, so just let me tell you. So basically you have a point P, you have a point W and you have point WW. Okay, and then you have something like E. Now if you want to calculate at the face W, at the west face you want to calculate the temperature. Okay, so and assuming that the flow is in positive x direction, so basically this WW will become upstream of upstream, W will become upstream, P will become downstream and E will become downstream of downstream. Okay, this is the notations which we have to understand how I have written this. Okay, so this is the upstream direction because I am assuming that the flow is in the positive x direction, and so WW will become upstream of upstream, W will become upstream because I am looking from west face. Okay, so this is my border. Okay, from this whatever is in the left side upstream, whatever is in the right side that is downstream. Okay, because the flow is in positive direction. Now as I said earlier, I need 3 points. Okay, and I need to take into account more of upstream directions. Okay, so what I do is I start x from my upstream of upstream. Okay, I intend to take these 3 points. Okay, upstream of upstream, upstream and one downstream point. Okay, so I write x equal to 0. What is my temperature? Temperature is equal to temperature of upstream grid point, that is WW. Okay, now at x equal to delta x, now you come from here to here, right? Delta x, this is delta x distance. At x equal to delta x, temperature is equal to temperature upstream. Similarly at x equal to 2 delta x, okay, temperature is equal to temperature downstream, which is equal to temperature at P. Okay, this is equal to temperature at W, this is temperature WW. Okay, this is how you have to do. Okay, now substitute these three things: x equal to 0, temperature is this. Okay, right, temperature is upstream of upstream, which is equal to C. Directly I got the C value, right, because at x equal to 0 I'm substituting. Okay, now you need again two equation. Temp stream of upstream is equal to A into delta x whole square. X is delta x, so plus B into delta x plus C value you already know, temperature of upstream. So you have one equation, you will get another equation for TD. So you have two equations and two unknowns A and B, solve them, you will get A and B. So that is how you come up with a general equation for t, okay, at the face. So this is how you derive it, okay. So it will take 5 minutes, okay, but try to always derive things like this, okay. Otherwise if you try to remember this, because what usually people write, directly in textbooks also, I mean derivation will be given, but finally they will give in tabular format, like they will give T at any phase is equal to W1 of T upstream plus W2 of T upstream plus W3 of T downstream, and this weight values are given in terms of delta x, okay. That is the convention way in which it is given, and sometimes it comes as a ratio of delta x values. So usually if delta x is same across all the cells, usually they write directly in terms of number like 3 by 2 minus 1 by 2, something like that, okay. Minus 1 or something like that, so it should actually become equal to 0 or something, I don't know. So they write it like this, okay. But you have to always come from this basic approach. Now for this is for quick. If you do second order of point, it is more easy, okay. It is just ax plus b, second order of point, okay. Although name is second order of point, it is actually first order scheme, okay. So here it uses two grid points, okay. So that is the way in which you derive. So anyway, so that is how the things are, and here the answer should be 3, as you have already answered. So let us come to Siva's question, okay. How does the delta x value affect the cell Peclet number? Okay, so this is the last question. After this we will discuss the code directly, okay. um, Find the appropriate scheme for fluid flow with density 5, velocity 1.5, length 10. Domain is discretized with 1000 cell, diffusion coefficient is so and so. Okay, so to decide the scheme, as I said earlier, we need to know the Peclet number. What is the influence of the convective force? Okay, if that is more, then we have to go for a upwind scheme, or else we can stick with a central scheme. Hybrid scheme, power scheme, they are usually used at border, okay, near when the value is near 2, okay. Usually there these schemes are used. Otherwise if the value is very less than 2, less than 1, say less than 2, I mean it's not even in the border, it is very less, so usually central scheme are used. And if it's greater than, it is largely deviating from 2, higher than that, first order of point, or else any upwind schemes are used, okay. So we need to calculate the cell Peclet number. These are the given things. The Peclet number you already know, Fc by Fd, and this is for the momentum, it is not for temperature, okay. Because this velocity, density and all are given, diffusion coefficient is given in terms of this for flow, okay. So Fc will be rho u, okay. Now you calculate it as 5 into 1.5, 7.5. Now FD will be tau by delta x, okay. So because I think you have already seen this, okay, while deriving we had tau into d phi by dx, okay. So basically we took tau by delta x as one thing, and then the delta phi as the other thing, that is in terms of phi it comes in. Whatever is left out apart from phi, that all those things we call it as fd. Similarly in the convection part also we do, we take out phi common, we remove out phi, and then whatever is left out behind that, that we call it as fc, okay. In for x momentum you will get only rho u, okay, there, okay. So rho u came in for fc. For fd we got similarly tau by delta x, so that is why it is tau by delta x, okay. This is where delta x comes into picture. So is that understood? Fd is given wrongly, so okay. What was the equation for FD? I mean, how was the FD defined? I don't remember. Can you write down on the chat box? I think this should be the correct thing. Tau into delta x. No, no, it should be tau by delta x. Was it given tau into delta x? I don't know. It should not be tau into delta x. It should be tau by delta x. Um, because I think I have written it somewhere here. Let me just check. Huh. So if you see in this question, So we have here like for diffusion term. This is for diffusion only, anyways. So this, but this is for your this is for your temperature thing. Okay, so here you have TE separated, you have Ka by delta x. Again, A is removed out. Okay, A is common everywhere, so usually if the area is common, so it is usually K by delta x. Okay, now K is nothing but diffusion, in again generally it is called diffusion coefficient. Okay, K, so it is K divided by delta x, it is not K into delta x. Maybe there was some printing mistake, or I don't know, but I think it should be divided by delta x. Okay, okay. So let us see. So it should be tau divided by delta x. So you get up with Peclet number of 0.75. Okay, why? Because FC came out 7.5 and FD 10, so 7.5 divided by 10. Okay, so it is, since it is less than 2, it is what do you say? What should be the answer? So the answer for last question. You mean question number 7? I asked. You're asking question number 7 or 8? The 8 I am discussing now. Anyway. Okay, so for question number 8, so it is less than 2. So what should be the answer? What scheme will you use? Okay, okay, central. Yeah, so central is the correct answer. So if say I had only say 100 cells, what would be your answer? Everything remaining the same, only if the number of cells that would have been 100, only instead of 1000 you put 100 here. Okay, so what would have happened? Zero point 0.1 into 100 divided by 10, sorry, here, zero point 0.1 into 100 divided by 10, so that is 10 divided by 10. Okay, that would be 1. Okay, so you have FD as 1 and FC as 7.5. So what scheme would you use in that case? Can you write on the chat box if n was 10, n was 100? Okay, it would be just 7.5 divided by 1. Okay, 7.5 divided by 1 would give me Peclet number of 7.5, which is much greater than 2. I would go for a point scheme. So always remember, it's not only about your flow, magnitude, direction or what. You have to always check with the grid also. Okay, that also matters. So this might seem a bit counterintuitive, but it is the flow of information that also matters. Okay, that is kind of what do you say, determined by your grid spacing, the flow of your information, and this you will particularly learn in time marching schemes, wherein we will see CFL conditions later on. So there also the grid spacing will matter to a very large extent. Okay, so that is why even that will also matter. Okay, so this you have to keep in mind. Okay, with this let us complete this assignment questions, and let us try to solve a code. I mean, let us try to solve a simple problem, 2D problem using code, finite volume code. So this is one more important agenda which I have set for this course. Like, you need to also do some coding, understand CFD through that perspective also, not only solving this question and answers. Okay, this might not be there in the exam, this will not come in your exams, so this is completely optional. Okay, I would say. Are there any queries till this point? If there are any queries, just write on the chat box. I think Siva had a question regarding this delta x. Siva, is this understood now? This cell Peclet number dependence on delta x. Can you just write down on the chat box? Okay, thanks. Okay, so let us try to implement a finite volume method. Let us try to develop a solver for temperature conduction equation, heat conduction equation on a 2D domain. Okay, so last time we had done a 1D domain and that was using transient. That is much more easier. Now here it offers some challenge to us. 2D as well as the steady state offers both. Both of them offer challenge. Okay. So now I'm taking just a rectangular or a square domain as I said earlier. Okay. I am differentiating it into four equal grid points, four control volumes. Okay. So this is the first step. Select the domain. Now I have selected L is equal to 1 cross 1 and then divide the domain into small control volumes. Okay. Now for this I want to determine the temperature inside this plate. Okay. So this is typically say it can be used in your what do you say, heat exchange things wherein you have placed a plate and where the heat transfer is occurring. I mean, if I try to relate it to some practical situations, just that say for example in a manufacturing industry you have a bridge which is made up of metal slab, and on the one end of the slab you have say a temperature of 0 degree, now let us say 100 degree. Now in the other part you have temperature of 200 degree, say like something like this. Then how would the temperature vary within the bridge, that you want to try to analyze. So this is some practical situation, but anyway our problem is something like this. Okay, so I have boundary conditions like t is equal to 100, 200, t is equal to 300. Okay, these are the boundary condition, and t is equal to 400. Later I will just give a hint when you have insulated boundary conditions and all, or convective boundary conditions, that also how we can implement. But this is simple case, and first we have to generate the control volumes. Okay, inside this. Okay, so totally 16 internal control volumes, internal centroids will be having, internal nodes you can say, and then we will also have boundary nodes. Okay, now you will have a boundary here, boundary here, boundary here, boundary here, here also you will have. So I am drawing it slightly elliptical because this is not a normal node, it is a boundary node. Okay, this is very important. This sets apart finite volume from finite difference. Okay, this is the whole thing here. Now this distance will be something like delta x by 2, but we will take care of that in the code directly. I will show you how. But anyway, so this is the way in which we generate the mesh and all. Okay, now I'll just tell the difference. In finite difference method, what we did is we just took this governing equation k d square t by dx square plus k d square t by dy square is equal to 0. Okay, now what we did, we just applied a central differencing for this whole term and then came up with a linear algebraic equation. But in the finite volume method, we are more of a physical sense we take in. We say that this whole governing equation should be applicable in the control volume, so let us integrate it, then let us apply the this thing, what do you say, the Gauss divergence, and then try to convert it into surface integral. Now you get k dt by dx along east face minus the west face. Okay, k dt by dx the west face. Okay, now again you also have k dt by dy, right, plus north face. Now you will not get dt by dx along north face. Why? Can you write on the chat box? Why you will not get k dt by dx along north face? And inversely, k dt by dy along east and west face. We will not get that. For this Cartesian problem, huh? Simple Cartesian problem is equal to 0. Okay, why we will not get it's a 2D, but we can also get k dt by dx along north also, no? Why don't we get that? So you have to remember it's the dot product. I told you there is something called n cap dot dA vector. Okay. Now when you take dt by dx, it is the flux in the x direction. So and the normal here for this east phase, the normal will be pointing towards x direction. So it will be I cap dot I cap, which is 1. Okay. So that is why dt by dx will come. Now here also dt by dx will come. Okay, dt by dx will come, but it will be what will it be? It will be I cap dot j cap, because the normal will be in the y direction, right? So I cap dot j cap will become 0. So you will that is why I said it is a dot product of two vectors here, n cap dot dA, when you do the integral. So that is why you will not come up with dt by dx along north. Okay, dt by dy, again this is j cap dot j cap, then it will come as 1 here. Okay, I am eliminating the area, okay, because study state heat conduction without involving any heat generation. So area is say equal everywhere. So I am just removing that. I mean, you can remove k also here, because you can see that k is constant. It will get eliminated. So it's just this. Okay. Now dt by dx, I will just write it as te minus tp and all those things divided by, what should be this, dx. So it is something like this. Okay. This is P, this is E, okay, and distance, this distance is dx, what I have called it as dxe, okay, this distance is delta x. Okay, this will be helpful when you do non-uniform grid. Okay, you can, here it will be same, but one more thing is when we come here to this grid points, that dx w, okay, that what it will happen is it will become actual this delta x divided by 2. So that is why I have kept two different notations, so that we can automatically take care of this. Okay, so this will be in general dxe. Okay, so and then dt by dx along west phase will be tp minus tw divided by dxw. Okay, so similarly n and s, okay, so and so is equal to 0. Okay, so we will combine this tp values and write it as like ap into tp is equal to ae into te, t capital E, okay, plus aw into capital tw. Okay, so an tn ts or something like this. So ae or w or n or s, whatever it is, here you will get it as 1 divided by dx, small dx, e or w or n or s. Okay, so if you do the maths, okay, this is the whole thing, ae, aw, an, as, and then ap, you already know it is nothing but the sum of this af. F is equal to east, west, north, south. Okay, this is the whole thing, this is the whole code. Okay, now I have to just solve. I have to write tp is equal to what? tp is equal to this whole sum divided by ap, right? So that is my code. Okay, I'll just open the MATLAB. But what is more important here is to calculate these values of dx, delta x, and the dxe, dxw terms. Okay, because we have to incorporate this small thing here, which is very important, although it looks small, that here it is dx by 2 it will become. Okay, so the general strategy which I follow is that first I define these points. Okay, so let me draw from fresh. Okay, until then this MATLAB will load. My strategy is something like this. I mean, you can have a different strategy, no problem. This is what I am more comfortable with. Okay, so this, if this is my domain and control volume, so I do define x and y values here first. This is easy to generate. So for example, if I have 3 control volumes, I will get 4 corner grid points, something like this whatever I have marked as x. Okay, from these I just call it as x and y. Okay, in general. These I call it as x and y. In my code also you will see like that. Now this is centroid. Okay, this is centroid, this is centroid. Okay, for 3 control volumes you will get 5 centroids. Okay, so in general, say for example, if I want 20 control volumes, I have to define 22 centroids. Okay, plus 2. Okay, because here I have 3 control volumes and I have 5 centroids, right? 3 internal centroids and 2 boundary centroids. Okay, so this I will call it as xc, x of centroid and y of centroid. This is how I usually name it. Okay, xc and yc. Whereas this I just grid points, corner grid points, I write it as x and y. Okay, you can follow any convention, but this is general thing. Okay, so I have to define x first. Okay, from x I calculate xc. Okay, that you can see here. First I define x value here and here, and then I get the xc for this as just the average of x over this grid point and this grid point. Average will give me xc over this grid point. Okay, that is x y and xc yc. Now once I calculate xy xc yc, I can calculate the width of this control volume, capital delta X, and then I can define dx, E and W. Okay, and then dy n and s, dy n and s. Okay, this is the whole thing which I need. This is just the pre-processing part. Okay, so this is very important. If I calculate them perfectly, then everything, my code will work perfectly. Okay, so I have written a code, but I'll just try to take it in parts and then explain it and then just run it. Okay, and then I'll be just sharing this code with you all also. Okay, my laptop is, I think, a bit slowing up. Just hang on for a moment. Okay, are there any queries with respect to this? I mean, the way in which I generate the grid. So this is, first you have to understand that how you generate this grid, how you take n value. Okay, so whenever you want, say, 100 control volumes, you have to take 102 n as 102 plus 2 you have to take. Okay, is this thing understood? Any queries? Let me know. Okay, so that is what I have, that is the first step. Okay, I am just writing those steps so that you can understand. Okay, here I hope my screen is visible and this code is also visible. Okay, domain generation and grid points calculation. Okay, so lx is length along x direction, length along y direction 1, and nx, say I'll take, let me take 22, so 20 control volumes. Okay, 20 cvs I'll write. Okay, this is understood, right? Okay, so then what is the next step? What is the next step? Can you write on the chat box? Once I do this nx, ny and lx and ly. So the next step is to calculate the coordinates x, y and xc, yc. Calculate them. Okay, so that is the next step. So here I have just written it in loop form. You can more make it what do you say, vectorized form and all more, but this will be better to understand. Okay, so first I am calculating x, and for example in my case j is the x direction. Okay, because in your MATLAB j is taken as the column and usually I is taken as row. If I write t of I comma j, I will be row and j will be column. So column corresponds to x direction and row corresponds to y direction, right? So that is why I have written I as 1 to ny minus 1 and j as 1 to nx minus 1. Okay, so then I write j, x in terms of j, I mean x as a array of j, because x is in x direction and j is in x direction, so the x of j. Okay, so this is how I have written. So with this what I will get is, I will get x varying from 0 to 1. Okay, from when index is 1, because MATLAB index starts from 1, it will be 0, x will be 0, and when the index will be, say, nx minus 1, So what will happen is this x will become 1. Similarly y, I have defined y. Okay, now next step is to define, what do you say, xc and yc. Here you have to be very careful. Okay, here I will explain what I am doing here. Okay, calculation of xc and yc is quite tricky. Okay, so now what I told here is that xc I calculate it as average of these two grid points x values. Okay, so that is quite understandable. So this is the average. Okay, xc, and similarly yc also, yc will be average of these two grid points I and I plus 1. Okay, whereas xc will be average of j and j plus 1. Okay, right, and yc will be average of I and I plus 1. Okay, so that is true for internal centroids. These are internal centroids. Okay, so just let me draw it again. This is an internal centroid with a square. This is a border centroid. Now if j is equal to 1, now xc will be nothing but x of 1 only. It will not be average. Okay, because grid point is also here only, our grid point. This x is like the corner grid point. X is like corner grid point. This circle is like centroid. This is internal. I don't have to worry, but only the border I have to be very careful. So I have written that only here. Okay, if j is equal to 1, then xc is nothing but x of j, and if j is equal to nx, and then the xc will be x of j minus 1. Because if you remember here, we have seen that for 3 control volumes I'll get 4 corner grid points, 1 2 3 4, whereas I'll get 5 centroids. Okay, so that is why minus 1 is coming here. In other points it is nothing but the average. So this is quite clear to you. I think this is understandable. Xc is nothing but the average. So similarly I have done for y also. If I is equal to 1 or if I is equal to ny, just directly take the y, otherwise do the averaging. Okay, so I think till here it is understood. Okay, if there are any queries, just write down on the chat box. Okay, now this is very important. Now uh, after you calculate x and y for a finite volume grid, you have to calculate what is del x and what is dy. So del x is the width of that particular control volume in x direction, del y in y direction. So as you can see, just this del x will be what, width of this control volume, right? So it will be nothing but x of j plus 1 x. Okay, corner x of j plus 1 minus j. Okay, delta x, that will be delta x. But if you see dx, say at the east face, it will be xc of j plus 1, right? You are taking between two centroids, the distance between two centroids, that I am denoting by dx. So dxe, it will be between centroids, the distance between the centroids, so j plus 1 and j. And here similarly for west face, j and j minus 1. Only del x we can directly calculate using x. Now with this approach, what you are doing is directly, if the value at 2 if you come, it is directly taking, it will be directly taking half. Okay, because if you see xc at 2 and xc at 1, if you minus it, subtract it, then you are directly getting this delta x divided by 2 only. You did not explicitly write that. That is directly taken into account, and this is applicable for non-uniform grid also, this code. Okay, so that's the whole thing. That is how you define. Now once this is done, your code is done. Then just boundary conditions I am writing it as here. Okay, these are just the boundary conditions for the indexes. I am just writing them. Okay, boundary conditions. Okay, so t north, east, south and west, that is I have defined it here, right? Where did it go? 100, 200, 300 and 400. I think that is what, 100, 200, 300, 400. I have written it down like this. Okay, so now I am assigning them. Okay, ts, if j is equal to if I is equal to 1, that is south boundary. If I is equal to ny, okay, here I'll just write it as south, here it is north, because I is nothing but ny here. Okay, understood. So this is how you write it. So just go through this procedure. I mean, the way in which I am doing it. First, I have defined the xy values, then the centroid values, and then geometric parameters I calculated. Then initialization. Then the final step is calculation of temperature. Okay. Now, just forget everything. So just as I said earlier, T will be equal to this AE TE plus AW TW AN TN plus AS TS divided by AP, right? That is what I had written here. Yes, what it will be, TP is equal to AE TE plus AW TW plus so on divided by AP. So that is what I have written here expression. Okay, T is equal to 1 upon AP into so and so. And then I have defined this AE values for all the over the whole loop inside the domain. And why I have taken 2 and ny minus 1? 1 is nothing but my boundary, and ny will be also my boundary, nx will be my boundary. So there I am not writing this, calculating this. Okay. So this is how I calculate. Now you might say, what is this? Because we get a system of equations which we have to do matrix inversion and all, we have to solve that. But in CFD we don't do that. That is a very costly procedure. So we use some iterative schemes. I mean, this you might learn in next lecture or something. So here I have just used just a very simple iterative scheme. In technical terms it is called Gauss-Seidel, but what it does is that it just calculates the temperature values using the known temperature values at the previous iteration. Okay, this T whatever is there at the iteration, at the current iteration, it uses those values and calculates the temperature. And once it has calculated temperature like this, it checks what is the difference with the old iteration. Okay, T minus T old. T old is the previous iteration temperature. Now if the difference between the two iterations, if they come closer, less than 10 raised to 6, then the loop will get exited. Otherwise this while loop will go on till we reach an iteration wherein the difference between two iteration temperature value, it converges. Okay, so that is a simple thing. I mean, you might understand it in a much better way. If I tell Gauss Seidel, you will get confused. Okay, so I don't want to say that. It's just that, see, it is like a time level you can consider. It's not a time level, but you can, for understanding, you can consider. I'm using the old time level temperatures. Okay, um, and then trying to calculate something at new time level, and I am just comparing between two time levels. If they are close to zero, I mean if they are same, then I am exiting out of the loop. Okay, so this is it. This is the whole code. AE, I have explained already how I have calculated it. Okay, and in this B is 0 because we don't have any heat generation. Okay, so this is the whole code. I mean, if you run it, and finally in MATLAB there is a function contour. What it will do is it will give the contour of the temperature values. Okay, so contour field over XC and YC, those are my centroids, right? I have to plot the temperature values at this centroid, and this 30 indicates the number of color levels. Okay, it's just that. So basically if I run this code, you will see the contours coming in. So are there any queries with respect to this code? You can write on the chat box, or else I will maybe can allow you speak also. Yeah, so this is the result. So this is the I hope you are able to see this contour of temperature. Okay, so basically we had specified that the temperature along, okay, let me put the legend. On, like, on the west face I had some temperature values, on the south face it is same. So you can see that there is only one color, I'm not able to get this legend. Okay, so on the bottom you have one color, on the right side you have only one color here, that corresponds to only one temperature. Okay, you got it now. Okay, so it corresponds to 100 degrees Celsius on the north, and this maybe corresponds to 200 degree on this east, and south 300, and this west 400. Okay, so that is the legend. So then it varies linearly, something like this. In between, if I point it over here, it will be 267 Kelvin or something like that. Okay, so this is the variation. You can verify it using analytical solution also. It will involve your Bessel functions and all the analytical solution. You can check with that also. Okay, so this is how you write the code. If there are any queries, okay, I see a message. Why is it max? Okay, it is because it is a 2D array, right? Temperature is a 2D array now. So only if I take max, it will return me a 1D array. So what the MATLAB usually does is that, see, I have like 2D array points now. I have along rows and columns like this values. So values are stored like this in matrix basically. So if I take max, it will take max along this column, max along this column, max along this column, and store it as again 1D array. Okay, it will be like, okay, it will be like 2 3 4. If I have, it will store 4 here. Similarly, it will store 5 here. So again, I will get a 1D array 4 5 6. Again, I have to take the max of this 1D array. So that is why 2 times max. Okay, any other queries? I mean, you can unmute yourself and also you can say, I have allowed this. Okay, microphone access. This I am solving a pure diffusion equation here. Okay, uh, central approximation relate to unphysical. Where central approximation you are talking? Have you used central approximation only? Central difference. I mean, and I am solving a diffusion equation only. Here. Pure diffusion. You can unmute and speak. Okay, because I did not get central approximation leads to unphysical results. I have used central approximation. I mean, central difference only here. It's not leading to unphysical results. It is physical result only. In if you want to ask me about convection, so no, it doesn't lead to unphysical results given the Peclet number less than 2. Okay. In convection, you can still use central difference. Okay. Central approximation, you can use it if the convective force is less. I mean, if the Peclet number goes below 2, it will not give unphysical results. I have used that central difference also. Okay. What you are saying, that will give good results. Actually, that is more stable. Why we use central approximation is because it is more stable. If you see these upwinding schemes, especially I have used quick scheme also. Quick scheme is very unstable, although it is more accurate and all those things. But accuracy is one thing and stability is one more thing. These are not, they are not very stable things. Okay, and definitely we get physical results with central approximation also. Yeah, Vikas, you can unmute yourself and ask me. Hey, wait 1 second. Are you speaking something? I'm not able to hear. Ha 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 ha. Yeah. Yeah. Hello. Hello.
Actually, my question was regarding the content in week 4,
Huh.
where we have solved one-dimensional steady-state heat diffusion equation,
Huh.
and there was the boundary condition that at PA, at the initial boundary was 100, and PB that is 400. But when we derived all the formula and we get the temperature at 5 different nodes, the T5 represents as 460. But as of the boundariness, can it be possible, like if the boundary condition is 400, the node just before the boundary
Mhm.
is representing 460 as the temperature? Is it possible?
No, 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 no. If you have temperature at the left end and if you have a temperature at the right end fixed, okay, so that is
Yes.
your case, right? 400 and 100, whatever it is. And if you do not have any heat generation, you do not have any heat generation, right? In the problem,
Right.
then it should be bounded. It should be within the 100 to 400 range. It cannot go beyond that.
Okay.
I mean,
And the
in
condition.
your CFD, you can say I have taken only 4 grid points, and then if I am getting that, you can get that in CFD. Okay, I mean you can get unbounded solution when you, especially when you are taking very coarse grid and all. Okay, but it is unphysical. It is an unphysical result. The reality is not like that.
So we need to like be aware of the boundedness that this result is not
Yeah,
appropriate for that.
yeah. Physically, it is not possible. So it is an unphysical result.
Thank
Huh. So any other queries regarding this code and all? So are you able to understand the codes? I mean, what I am writing, or are you feeling it a little complicated or something like that? I mean, I think today only this XCYC you have to take care, but apart from that, it was easy. Okay. Any comments which you want to give me on code part, especially? Okay, so we will do this coding exercises. We will continue this coding exercises. Okay, in the next week, we will try to solve a vorticity stream function next, which is very much close to your fluid flow solutions, especially for 2D cases. I mean, you can obtain the solutions using the vorticity stream function approach. It is a very simple equation. Solving that will help you to get the flow variables. That is like just one step below the ultimate thing. The ultimate thing is to solve the Navier-Stokes equation. That maybe we'll doing it in maybe in 6th or 7th week or something like that. Okay, so that's the main steps of this thing. You have to start writing codes. Okay, you have taken this course, and these codes or something like this will not come into your exams or something, but this is what is expected out of a person who learns CFT. Okay, that you write codes for equations, and if you have to learn, you have to take baby steps. Okay, I mean, what platform from where we can practice codes? I mean, I did not get you. What platform means? You are asking me software or what?
you. No, actually I'm asking like the codes are not that much understable till now, so I need to like practice it.
Ah.
So for that, is there any source from where I can get the codes and run them and analyze it, how it is working?
No, these codes I am uploading anyways. Okay, so these codes I am uploading on the Google Drive. You can use them. You can just see them. Okay, but apart from that, if you want, I mean, codes for general Laplace equation or something, you can definitely search them. But I would say there is never a specific website wherein you will kind of get every codes or something like that. But you have to just I mean casually search over the web. You will get codes for like for Laplace equation, general diffusion equation, or something like that. But these codes anyway I am sharing, so you can just take them and just copy in part by part and then try to run them. Like X and Y, first you copy them and run them, and then see how X and Y is arranged. Okay, so that you can see, and then go to calculate the geometric parameters, the delta X, delta Y values, and then see the temperature. Okay, that is what I would say. Always start from simple equations. So that is what I am doing. Like last week I solved 1D equation, so this week 2D equations. Okay, that is for just an energy equation. Now next we will go slowly into the vorticity stream function equation. Okay, so always go step by step. And one thing, transient equations are more easy to solve. Again, the steady state, I have to use Gauss Seidel. Okay, I did not explicitly mention that, but if it was a transient equation, you would have understood it in a much better way. Okay. Okay, if there are no queries, thank you for attending. Okay, you can leave the class now. Okay, if you have any queries, you can write a mail to me. Okay, and just maybe give a feedback also. Okay, yeah, thank you.